Hello and welcome to this lesson on using rates of change to create a graphical model. Today you're going to be reading descriptions of different situations that are realistic or not, and creating a graph, usually distance versus time or speed versus time, to show the reader and the person that you're trying to communicate to a visual interpretation of their rate of change over a certain period of time. So you'll either be reading a description and creating the graph, or from a graph be making conclusions from that. So let's start with question 1. Today Steve walked to his part-time job. As he started walking, he sped up for 3 minutes. So I like to highlight important information as I go. Then he walked at a constant pace for another 2 minutes. When he realized that he would be early for work, he slowed down. His walk ended and he came to a complete stop once he reached his destination 10 minutes after he started. So what would the speed versus time graph of Steve's walk to work look like? So we're going to have two solutions, solution A and solution B. So the first thing you want to do is take your ruler and do your speed versus time graph. Okay, I always start by labeling my graph with the appropriate variables. So we have time here as the independent variable, and it's given to us in, minutes. And then we have speed as the dependent variable. And notice we're not given an actual number for speed, it's just increasing, constant, or decreasing. Okay, so we do know the time is a total time of 10 minutes, so we want to make sure we have a good scale here for 10 minutes. So I didn't draw it quite long enough for a good scale here. Okay. All right, so once you have that all set up, then I'll just label everyone just so it's not as, every other one just so it's not as cluttered. I like to do that. So 2, 4, 6, 8, 10. Okay, so what happens to the speed? Well, in this solution, we're going to assume his increase or decrease was at a constant rate. So think about how that would vary, okay? Whether it's a constant rate of increase or decrease versus a not constant rate of increase or decrease, so a varying rate. So as he started walking, he sped up for 3 minutes. So we can assume that at 0 time, he was at 0 speed. And then for 3 minutes, so up to here, we don't know how fast he went, but the speed was increasing. So because we're assuming a constant rate of increase or decrease, this will be a straight line. Okay, so it's increasing from 0 to 3 minutes. His speed is going up. Okay, then he walked at a constant pace for 2 minutes. So between 3 and 5 minutes, his pace was constant. So his speed stayed the same. Okay, and then he slowed down until his walk ended at 10 minutes. So from 5 minutes to 10 minutes, his speed was decreasing. So there we go, a nice interpretation of Steve's walk. However, how would this change if his walk was, if his speed changes at a variable rate? So go down to solution B, okay, and we're going to draw the same thing again. And I want you to think about, as you're drawing that, what's going to change from solution A to solution B. So with solution B here, we're going to assume his speed changes at a variable rate. Okay, so we still need to use a ruler here or a straight edge to draw our graph. We still need 10 seconds for our time. Okay, so time in minutes and speed. Okay, so what's different assuming that it's changing variably? Well, again, it said for the first 3 minutes his speed was increasing. So we're starting at 0 still and ending at 3 seconds, and it's going to increase. But because the rate of change is variable, we represent this with a curve as opposed to a straight line. So I'll do it something like this. Okay? But then we know from 3 to 5 minutes, so for those 2 minutes, he walked at a constant pace. So his speed is not changing there at all. So that is a horizontal straight line because the speed isn't changing. But then we have from 5 to 10 seconds, he was slowing down. But now we're again assuming that that's at a variable rate, so we can represent this with a curve. Something like that, okay? So, which details of the given description were most important for determining the shape of the graph? Well, number 1 is the timing, okay? Although we are not ever given any specific speeds, we were given specific times, and that's crucial to be able to draw at least somewhat of an accurate sketch. Second of all, we needed to know when speed increased or decreased. Okay, so over what time the speed increased or decreased. And we also needed to know when the speed was constant. Okay? So are these the only 2 graphs that could represent Steve's walk to work? Well, think about that for a minute. What has to remain the same no matter what? Well, between 3 to 5 seconds, that has to be a horizontal line, a straight line. But we don't know how high or low that line is because we aren't given an actual number for his speed, so we don't know. So that could be as high or low as we wanted, but as long as 3 to 5 seconds, the horizontal line. So we don't know that. And then between 0 and 3 seconds, as long as it's increasing, this could look different. You could have something that looks like this, or something that looks like this. It's not quite as shallow. Okay, so there's actually infinite number of positions from 0 to 3 seconds as long as it's increasing. Okay, same thing from 5 to 10 seconds. It could look something like this. Okay, as long as speed is decreasing, because that's the only information we're given. So to truly draw an accurate graph, you would need much more information. This is just an interpretation of the information that we were given. So again, there are many possibilities. Okay, that's your answer for here. As long as from 0 to 3 seconds, the speed is increasing. From 3 to 5 seconds, the speed is constant. And from 5 to 10 seconds, the speed is decreasing, ending at 10 seconds. Okay, so go ahead, as I'm erasing this, and take a look at this next question. I'd like you to pause the view for a moment and attempt this on your own, okay? You'll need 3 axes there, but I'd like you to try this on your own and then go ahead and see how I interpret it. So pause the tape. Okay, now that you've tried this on your own, I'll take this up with you. So a flask, a beaker, and a graduated cylinder are being filled with water. The rate at which the water flows from the top is the same when filling all 3 containers. So that means that the water coming out of the tap is at a constant rate for all of them. You're not changing the speed of the water. So draw possible water level versus time graphs for the three containers. So you should have all labeled these time versus height or water level, okay? You're not given units, so that's fine. Okay, so what you should be considering now is the shape of each of these and how that affects the water level. So, for the first one, time in seconds. At first, the water will be filling a larger area. So the height of this cylinder will be increasing gradually. But as you get up to the top, it will be increasing faster and faster and faster since this width here becomes less and less. And then finally, for the last little bit, it'll be a uniform time. So the height will increase over time at a constant rate because it's the same. So at the beginning, you start at 0, a height of 0, and it's increasing at a variable rate, but kind of slow at first. And then it will go faster and faster and faster, okay? And then at the end, you'll have an increase, but that should be a straight line there. Okay, so you should be increasing, but going quicker, and then end with a straight piece to show that this is a uniform width. With this one, it's a uniform width all the way to the top, okay? It depends if you include that little lip or not. If you're not including that little lip, let's say we're just filling to here, you're going to have a straight line. Oops. Because it's filling at a constant rate, okay? So the rate of the filling is constant, okay? And finally here, again, if you're filling just up to here, it's also a constant, but this height will increase much more quickly, which means a much steeper slope, okay? That's the difference. Okay, so a cycle is observed moving at a speed of 10 meters per second. She begins to slow down at a constant rate and 4 seconds later is at a speed of 5 meters per second. She continues to slow down at a different constant rate and finally comes to a stop 6 seconds later. Okay, so they want a time versus a speed versus time graph. So again, the first thing to do is label the axes with as much information as possible. So we know that time in this case is in seconds. And speed is in meters per second. Okay? So how much is our speed changing? So we have, obviously we start at 0 here. And the most that she ever goes to is 10 meters per second. So how do we represent that here? I did actually, what did I do? I did 3. So I did 3, 6, 9, 12. Just because I have room to do that. If you choose to do a different scale, that's fine. I just don't want it to look too smushed together. And then how much time do we need? Well, so this is 4 seconds later, and then 6 seconds later, so that's a total of 10 seconds. So 2, 4, 6, 8, 10. We need 10 seconds. Okay, so now let's go ahead and graph this. So she starts moving at 10 meters per second. So she starts here at 10. And she slows down at a constant rate for 4 seconds. And at 4 seconds, she's at 5. So at 4 seconds, she's at 5 meters per second. And in between that time, she's slowing down at a constant rate. So constant rate means that you could do a straight line. Okay, it's not a curve, it's a line, since that rate is constant. There you go. okay? Then she continues to slow down at a different constant rate for 10 seconds. So between 4 seconds and 6 seconds, again, it's a constant rate, so hopefully your ruler is long enough to reach. I'm going to have to kind of guess this a little bit. Oh, see, I didn't quite do that right. Let me try that again. You're basically just connecting this point with 10 to 0 because that's when she's stopping. Okay, so there should be a distinction here between this, how much this slopes and how much this slopes. Okay, so this point here is 0, 10. So at time 0, the speed is 10. This point here is 4, 5, and this point here is 10, 0. Okay, it's important that you label these points because we'll need that in a minute. All right, so what is the average rate of change in the first 4 seconds? So average rate of change, just remember that's the change in